So it's a pleasure to have Professor Judy Fox speak today. Judy is a longtime collaborator of a group. She used to be at Indiana University and has since moved to UVA in the School of Data Science, and has been doing some very interesting work at the intersection of edge computing, HPC, and recently on privacy-preserving models. So Judy, over to you. Thank you very much for giving the talk.
Thank you, Amada, for the introduction. I'm Judy Fox. I just joined the UVA almost 8 months ago. So I want to update you on our recent research work, and this is based on our recent publication. The topic itself is related to privacy preserving computing. I was mostly interested in many areas. My focus is coming from computer systems, and you can see that there are many elements I've been working on over the last 20 years. Specifically, I work on computer system intersection with big data. That incorporates many high-performance computing models, applications, and the aspects related to education. One of the areas over the years I've learned a lot is the growing importance of machine learning, in particular deep learning. And all of our NSF-funded projects, including also other industry and NIH project, is related in these areas. So we learned from the big data applications is the centerpiece of the next 5 to 10 years. And in computing aspects, we grow from the batch-based static processing to more dynamic scheduling and streaming applications. From the computing hardware aspects, we can see the increasing growth of CPU cores and the GPU accelerators playing a central role in the AI space. Cloud is dominant in over 90% of the computing resources from the industry. We can see all of this area make a tremendous transformative impact for all fields of science and technology. So I feel myself, even given the position of data science, the integration, how to orchestrate, coordinate this together as the effective method, that is my heart of my role to help the community moving forward. I have done many interesting projects over the time, and I'm really appreciative that all my collaborators in different fields, this including the graph analytics. I've working many years with initially Virginia Tech, but now Virginia and other collaborators in building the graph analytics libraries. Recently, I've also worked in streaming data analysis with IndyCar, a company for anomaly detection. That is a very interesting distributed streaming real-time machine learning applications for time series. Current work is related to the security. This is coming from human genomes analysis and the alike. Has a lot of privacy preserving data issue, not only related to genomics, but technology and other fields all have the common problems. So my focus in this talk will cover the top 3 areas, in particularly the library kernels and security aspects for the frameworks. So this working with a lot of colleagues, we work together, including our students and the collaborators, Professor Xiaofeng Wang and Professor Haishi Tang. They are experts in the field of security and bioinformatics. It turned out to be very interesting that they organized the competition in these areas. There were international participation in this secure privacy preserving algorithm optimizations. My contribution in this work is mainly in the computer system and the framework part. We worked on the Intel SGX hardware as an example to show how to make this system work for genomic computing. This paper comes from the recent years, people's realization of the importance of a global AI supercomputer concept. So this is a talk comes from Donald Kosman, who was from Microsoft. As an industry lead, a lot of cloud-based, AI-based company efforts, they realize the importance of the system work, incorporate a lot of privacy. It's not just sensors, Internet of Things, but related to a public cloud. There are many system work related to AI and the prediction and workload of a lot of synthetic workload. So that is the heterogeneity part of our work, and I'm focusing on. This across the software, the libraries, application, but also deeply related to hardware accelerators of the architectures. So privacy preserving computing is increasing important element. This is because a lot of our data is related to personal human genome, public health, financial related privacy client data, and all of this need protected to be able to use. Unfortunately, at the current state, the homomorphic encryption is computationally infeasible. And there's no practical solutions, even software and tools available in this space of privacy preserving computing. Our project is funded by NSF. It started 2.5 years ago. So this is the time that we make the progress. I want to report the detailed result in this talk. We find it is promising we can use hardware trusted execution environments called T and exemplified by SGX to utilize this hardware level security protection. And this is the way we're approaching security from bottom up that incorporated every level from library to middleware to application. We all need to make changes to make it work. So we use one use case, which is a BWA, is a risk mapping, which is gene sequence alignment algorithm and application as the foundation to exemplify our study. It turns out risk mapping is the very foundational algorithm that being used by all bioinformatics applications, and it has intensive computation that need privacy preserving components. So let's look at what is the mechanism as SGX and how does it work. The SGX is the hardware component on top of the regular memory. With this hardware support, one can access the memory with a trusted part, which is highlighted in this chart. On the other hand, we can leverage the regular memory size. One of the issues is how to protect the data with encryption, and when they process that, decrypt that, that is all happened in the enclave, which is a protected region here in SGX. There's a huge overhead moving data in and out of the protected memory region, and thankfulness because of the hardware level encryption decryption make it feasible. One major barrier in the current technology of T, in particular SGX, is that we have a limited memory size of trusted part. That is, in the model we're using is 257 megabytes. It's quite small compared to the application we want to execute. As an example, our human genome, the complete size is 3.2 gigabytes. So with this kind of a gap, how to bridge it becomes a challenging problem we're facing. And we also wanted to incorporate the security elements in there. We want to protect the software against attacks from any level of privilege, from the hardware level, from the OS level, library, and software. And also we want to protect the hardware attack space to not have the protocols of untrusted code dynamic loading the libraries. So their whole stack has many redesign and considerations. Related to our work is we come up with the idea is trying to address this very heterogeneous data set from secure data versus insecure data, and from the different components in the whole data analysis pipeline, we trying to find out a way to mitigate, bridge the gap. So this is the architecture chart to illustrate our way to address this. And if you can look at the non-secured hardware, it's a common CPU, GPU, and FPGA and as such. With the trusted hardware is SGX, and all of this is all independently working and a different kind of a configuration capabilities. So we unify them by using containers. For example, Kubernetes containers is very common infrastructure API from industry to academia. On top of that, we need to incorporate the components of security and utilize the best practice of graphing and SCORM. Those are different kind of computing libraries. They have a protection layer for access control, for how to integrate with the host operating systems. The difference between Scorn and graphene is based on operating system level virtualization. And Scorn is using the virtualization as a common, like the VM levels. This is quite important. I would not go to detail of each of this architecture, but the main issue is that they can facilitate port legacy code. As we know, a lot of scientific algorithm and industrial applications already existing and developed with a lot of effort. So if we can have a common generic infrastructure to port them to this hybrid, secure, preserving computation model, that's a huge leverage economically and functionally. So our work is focusing on separate secure versus insecure container, try to orchestrate with a middleware to scheduling all this workflow in a hybrid fashion. To illustrate that what has been done conventionally, this is one of the BWA applications with sequence analysis alignment application. One can see that all of this real world application quite complicated. We need to deal with how to use alignment of data, usually has to be indexed for real use and queries. And after that, we need to merge them so that we can get the outcome of the query result. The input data is coming from the database of the human genomes. Some part of that is publicly accessible, but on that part is a personal genome has to be protected. So it's a highly mix of all of the data and in a workflow with different components, including the different elements, even distribution, indexing, and then we have the Bloom filters to try to accelerate the query analysis. And then we do the alignment and merge with all this result. So with such a complex workflow of genomic computing example, how do we accomplish this with privacy preserving computing? We started with analyze the data, and it turns out, although the data size is huge, not all data need to be put into the enclave, which is quite small in memory. So what we do is that we try to distinguish the data need to be preserved securely and analyzed versus this data we can build outside in common memory space or execute in CPU. So after this split, clearly we can analyze that the pipeline with distinguished data is personal human genome data we will need to protect, and that only incorporates the part of the execution component, such as dispatch, alignment, and merge the outcome. And in between them, we need to deal with reading I/O with the file system, because a lot of the computation cannot do in one time. They have to load data through the memory hierarchy. So we have another element with encryption, decryption for the security, the computation models. The whole execution pipeline is fairly complicated. We have 14 steps going through each one of them. So there are such hybrid workflow. I want to emphasize is that common to a lot of applications in scientific analysis in health, particular, they have this data privacy issues. If we break down all of this computation, how do we leverage interface existing the security protection layer? This is where we try to utilize the hybrid mode. You can see that the index building in this BWA analysis, we can do it in the normal CPU space and in the regular memory. That is huge in size and it takes a long time. But the alignment part, we can incorporate the secure data set of human genome and then do the indexing by using partition and scaling horizontally. And you can see this can be done in the enclaves. And that enclaves are executing the library using either Scorn and graphene. They can load in on algorithms such as aligner into those frameworks. So we can execute them and then port the intermediate data out to the disk. And the next step, we aggregate all of this encrypted data and merge them and get the global result as a final output. Security analysis is fairly complicated. This incorporates into many elements in the operating system level because they need to check the integrity of loading of libraries. We use the safeguarded frameworks such as Scorn and graphene And that will be able to address many file encryption, decryption problem and intermediate data. We also try to leverage the thread model of the existing framework, and that is related to some of the side channels attacking issues that is my collaborators' work from Professor Xiaofeng Wang. One of the elements here related to high performance is dispatching. As you can imagine, a lot of this computation is incorporated into parallelism. So we have to partition the task, including the DNA sequence partition. Based on the hardware availability, we partition the size of the data and try to leverage some of this into our regular memory, and then reduce the size, use the Bloom filter optimization, only the relevant part loaded into the very small enclave memory. And you can see the whole mix of this is going between disk and regular memory and mix with enclave memory to leverage the optimized algorithm to speed up the performance. So the overhead, unfortunately, any secured related computing has a huge overhead because they move data in and out of the secured memory space. So the heap size of them varies a lot from the 16 megabytes to gigabytes. And we can see the hardware manufacturers continue to improve the size of the trusted base of memory. The one major overhead is the cost, the equal and all cores moving data into regular memory to the enclave memory. The common bottleneck is coming from the EPC is the cache part of the page swapping. This is very common in the memory hierarchy between the enclave memory and the page of the regular memory space. And currently we have the limitation of 128 megabytes. The real usage of our application only limited to 90 megabytes. You can imagine any computational algorithm calculating the processor is pretty small. Now I want to show you some experimental results from our work. This is the data set that we come from the 1000 Genome Project. This is gathering a lot of data internationally to create a common human genomic variations to study people's health. And we utilize those data as the base to do indexing of reference genomes. And a lot of this data set, we select a subset of them and using personal genome to do the queries. And you can see there are a lot of subset of the reads and the data sets from there. Without losing generosity, we can utilize this as examples. One of the areas we want to probe and detect the boundaries of current SGX hardware is to what extent we can optimize the hardware resources to execute our HySec-Flow framework. As we know, there's a gap between what the size we can access and the large size of human genome data is in gigabytes level, and the memory of the enclave size is only 19 megabytes. So with this understanding, we know how we leverage the distributed or parallel computation. We can partition the data to make sure that we can have multi-threading internally to one node, and the internode we can do partition between the processors. And with the size, we learned that 80 is the appropriate size that we can fit into the small memory size. But with this understanding, we do a comprehensive analysis, compare secured computation approach versus that without secured. You can see there's a huge overhead between the non-secured approach. And we can execute them in our case, the pipeline with 15 seconds using the data set we have and a subset of the human genome reference genomes. So this is the first time that we were able to make it closely feasible to using secured framework to do real-world genomics computation. To give you a detailed dive into the breakdown of the whole framework, where to spend time, you can see the total execution time, including the dispatch, alignment, and merge part. Those is deeply related with secured computation is shown here. It has a lot of time and a breakdown into this. So we use a graphing, contrasting using scorn and using a naive method with the SGX, the framework. You can see the overhead varies based on the software frameworks we use. And break down further into the dispatch part, we use a sequential contrast with parallel. We can see that we partition all the data and schedule hybridly the workflow, we can drastically reduce the computational time on the dispatch part in the parallel. So the part that we don't need to do in the secured enclave space, we can use partition, Bloom filter building, and the index, which is enormous time consuming. We can do it in the non-secured execution units. That is one way of doing the optimization in details. And the rest of the part is the alignment, and the merge part is less time consuming. So the major part is the dispatching and doing building index. So we have a mix of secured and insecure methods to deal with them. The speed up the HySec-Flow using the secured components, we can see the overall achievement is speed up of factor of 6 up to over 200 compared to just using the framework score and graphing. In other words, without the HySec-Flow, we're just using score, naive score and graphing. It doesn't scale as well, which is impractical to use in real privacy preserving and computing. And we can see that the increasing in the performance can be continually improved if we fine tune the computation with optimization at the parallelization and algorithm level, such as Bloom filter. To summarize, this is the architecture of an end-to-end workflow. We're trying to leverage hybrid containers to achieve the privacy-preserving data analysis at scale. And we utilize the Intel's SGX technology to put the secured data into the enclaves to port the legacy code for execution. And we can achieve up to 200 with 80 partitions of this secured computation compared to the naive approach using either score and the graphing. So the speed up comes from many levels of optimization. We look at the very detailed partition of a data size, and we look at the algorithm level optimization with put the minimum needed data into the enclave and reduce the search of the disk space. And we mix this computation of the non-secured part versus secured part, and in a hybrid fashion, to schedule them in the workflow. So there are many places we believe we can continue to improve the performance based on this work. Now I want to switch gears to talk about related applications that can benefit from this framework. The first I want to talk about is high-performance graph algorithms. So this is based on our earlier work related to computation kernels in graph analytics, because graph is a very important library or algorithms that can be used by social network, bioinformatics, and alike. One of the major challenges there is the linear algebra kernels sometimes is sparse. The workload is very random for in-memory access. So that makes the efficiency of these kernels hard to leverage the common GPU in particular and the CPU vector machines. So there's a huge gap between library versus the irregular access of the memory. So we utilize the optimization to identify the major kernels, sparse kernels, to optimize the algorithm, make them more regular. In this way, we can leverage the common libraries of sparse algorithms in graph, in particular, as a vectorizable, so that they can port as a standard library to CPU, GPU, TPU, and all other emerging accelerators. So this is part of the work we have done in collaboration with the NEC and other partners. So you can see the enormous improvement in performance after we use long vectors to vectorize the sparse algorithms. And I illustrate here is trying to link to how we leverage in the fairly complex graph algorithm into the secure or non-secure data related to epidemiology or the bioinformatics that we have knowledge already. So we wanted to move forward using these incentives. One of the major frameworks of build upon is a convergence of big data and high performance computing. Is rooted from the data parallel applications of data analysis. So there are many stages of the computation we can think about how to support moving forward with the parallelism for machine learning and how to do the iterations and for deep learnings. This is our earlier work to build toward the interoperable the data analysis workflows. The major idea here is that we want to break down the whole computation into the several powerful abstractions. At a very low level, we want the algorithm kernels to leverage existing work that's already high performance. And we leverage that port to different hardwares, including the CPU and GPU, all emerging hardware, even on the edge, because we have existing very rich libraries can run on those devices. The second level is that the abstraction of a computation model and illustrate we earlier our project HySec-Flow is doing synchronization within the node, but more importantly, a data movement of the internode in the cluster environment or distributed environment. On a very top level, we want to abstract out some of the algorithm and the workflow using generic middleware so that they can do task scheduling. So this kind of convergence between the low-level hardware, high-performance hardware, and the top level, the big data heterogeneity applications is the focus of our data-centric approach. There are many work has been already done in the space of computation models and patterns, and I will talk later on what the challenges has been proven to work. And this is in alignment with the existing HPC community already done in NPI. They have done a lot of gather group and all of this computation, and we add to the category by a lot of distributed computation, asynchronous computation like push-pull rotation, and so leverage the best of all these practices. There are many kernels in machine learning, and in particular deep learning, the workload, majorly the kernel of linear algebra is regular computation. A lot of data is not regular. So that adds a lot of complexity of choosing what is the right model for specific workload. So we have studied all of these combinations, when and where to use a different kind of machine learning, deep learning, and leverage the hardware features based on the computation need. To summarize, one of the foundational computation models coming from the synchronization and how sensitive all the convergence, such as deep learning, relevant to the data and how staleness and update of the data. So we have this different modes, the trade-off between the performance versus that the accuracy. So we have a lot of studies in a set of machine learning algorithms. I will show you shortly. So k-means, PCA, and the subgraphs are all common algorithms we use in the space. We compare the different computation, you leverage the framework we mentioned. And we can see this can run to the extent like complicated algorithm and on different CPU, GPUs by tuning all the parameters, workload, and different hardware and data size of these batches. There's a whole category of scalable algorithm implemented using our framework, and the classification come from the dimension reduction graph. And recently we have the work related to the deep learning, and all of this have a commonality in computation model. Fortunately, as a small subset, we can cover those different computation and in domains. The new area of applications related to deep learning, as we knew that the CoVAC is one of the critical applications a lot of this group is working on. We're looking at the CoVAC daily distribution and hope that we can have improved performance and accuracy. For this data set, we come from the collaborative work with University of Pittsburgh Health Center. So we utilize the CDC dataset, the US Census Bureau's dataset, and also the health datasets from NIH. All of this dataset have the common features, which is related, we can think about what to be secured. This coming from the static data, which doesn't change much over the time, and dynamic data is cumulative, the cases, as and transmission, testing, and spread, and the social distancing. A lot of us researchers in this group already shows their theoretical and computational work in these areas. A lot of algorithms in alignment with this. In our work, it's preliminary. We're trying to detect anomaly in the data itself because a lot of the data is very noisy, and we can see the global outliers existing at the county level over the time window of 2 weeks. So we first to smooth out the data by remove the global outliers. And then we started the dynamic and static data correlations using the heat map and try to see what is the possible insight into this hybrid static features versus the dynamic features. And we are trying to predict the infections over the daily cases from the last year to this year, April, and we got this data prediction of the death and the infection rate. So you can see that there's a spikes of dips we not predict well, but after smooth out the data, and it's getting much more improved in the prediction. And we studied the RSTM time series deep learning model versus the new fusion transformer model and try to see how they can leverage to get better result. So you can see that a lot of the counties, especially the top 500 counties, has a very dynamic features. So there's no one solution fits all. So we're trying to study and correlation of different cases in different counties. I want to switch gear to what we learned from all of this in relation to the work I'm moving forward working with Intel. Based on a lot of existing work, we can observe that the world is getting more dynamic and heterogeneous on their workload from the individual researchers, the labs, and the teams. And we need to utilize the common middleware and the framework to leverage existing libraries, programming interfaces to optimize them without that compromise their usage and port to the most cutting edge hardware. So this is the incentives that we want to use one API to unify all of these computations with several powerful abstractions. So we hope that will work out over the time. And the ideas behind that is that with increasing machine learning applied to many areas of the domains of science, we wanted to orchestrate or unify them by a common framework. And you can see there are so many existing tools and libraries in the space from open source to individual or private development, and it evolving over the time. And the computation only getting more complex. And the hardware is also an open area. There's a lot of changes, increasing the core numbers, reduce the size, and increasing the kind of capacity from large to small, from supercomputers to edge devices. With all these diverse options, how do we build the software to accommodate all this kind of a hybrid workload? That is a major challenge that we're facing as a community. So one observation is that we can play an important role over the years of study. We're building the data analysis, data-centric softwares. From our experience, we could look at the 3 levels of abstractions. One is the abstract of the vendors, and when vendors can provide different compilers of the details of their hardware instructions. So this is a low-level hardware independent abstraction layer. So we optimize the kernels, vector, the kernel algorithm to benefit, to leverage each of these different hardwares. The second layer is the middle level, is the algorithm. So we can try to leverage the kernels, optimize algorithms contributed from different domains. And when they execute their workload on data, we truly need something high-level framework, which is related to the talk here, is a task scheduling and independent of the frameworks using the scheduling. We also need to consider the secure data that add orthogonal elements to impact the whole design space on top of this. That is where we need to be able to accommodate the hybrid workload with secure and non-security in this middleware level. To illustrate parallelization to make it feasible for our computation needs within the kernel is simple. So we understand when we program application to specific size or workload, we can go inside into those data structure. We can leverage the arrays and high dimensional tensors. We can do this optimization. That's fairly easy to on the work item space, and they can do it once and for one time. However, if we want to map to a lot of data site with a different range, this becomes more complex because you have to control from the application level the data size matching to these common data structures. And we need to identify what is the range we want to partition. And that is where a lot of work needs to be done to expose the hardware so you can efficiently execute all those workloads. In real world, actually, it's not so simple. It's getting complex because the heterogeneity of the data structure, structured data, unstructured data with timestamps. And now we add a dimension of secured and unsecured data set. to achieve the high peak performance requires a lot of thoughts about how to leverage each level. And if we want to build generic abstractions to accommodate all of this, we come back to the basic computation model is SPM and D model for data parallel applications or algorithms. I think that might be the more generic approach for heterogeneity we can start with. A lot of abstractions work well, but there are some boundary cases they cannot accommodate. And that is the roadblocks for generalization to make it a uniform framework and approaches to work. We realized that the growing need in the specialized workload is universal in data-centric hardware requirements. Recently, we realized this is the top 500, the top 10 machines actually are heterogeneous machines. Not to mention a large field of size and in the domains they were needed for very specific accelerators to accommodate the need. This is our starting point, trying to see how we integrate this need together to bridge the gap. From system perspective, we talk about application incentives and frameworks. We have done a lot of work here. Our dream is trying to implement a system. It's a global supercomputer. No matter it's a large real supercomputer or it's a sensors device, we want to be able to handle the data challenge to make it running efficiently and accommodate heterogeneity. So we have already several abstractions explored over the time from across the data analysis landscape with tools. We leverage using the in-memory cache all those computations. We utilize the data flow frameworks to facilitate complex analysis. We're using concurrent threading model to aggregate and workload and to scaling vertically with the local computation. And then we do extensive internal communication to do distribution and then port to different languages. Now that most recent language is Python. And then we add in this work is data security. So that covers the landscape for the whole computation from a different level of the data analysis and abstractions. I think that from all of this work we have, we can try to think about what we can do moving forward. So one of the areas of interest could be the heterogeneous pool of using containers to facilitate the computation. And we try to integrate the high performance kernel libraries, port the existing domain work, and into integration of the workflow to facilitate the execution. One latest news I learned is that the Intel SGX will be available in their IceLake 10mm chips. So anybody who wants to execute the workload has the potential to be able to use the secured workflow to execute on their applications. And next year, they will have a new called Sapphire Rapid architectures, 7mm, and with the potential to increase the enclave memory size to gigabytes. It's a factor of over 100 level bigger. So what all this says that we have the potential to make it realistic at usable or production level secured computation to make it possible. And this is where I want to bridge the gap between our framework and our over the years of the work to integrate with the one API framework so that we can have a true hybrid workflow to facilitate secured computation and non-secured computation. This work is illustrated by the genomic computing workflow, but many other computation will have similar features that we can express and use. I actually wanted to take this opportunity to acknowledge our funding agencies. In particular, we have funded by NSF on the big data project to enable us to do this work on privacy preserving hardware level computation. And we also want to thank that the expedition project give us the incentives of how we try to address this ongoing COVID studies, the epidemic computation related to our existing work with the graph community and the complex systems. Finally, this work is also funded by my collaborators, Professor HEintroduces and HEintroduces, related to privacy preserving and funded by NIH. So we got a lot of support from Intel. We have recently quite a few meetings on how to move forward to leverage this. And I'll be really happy to learn what your aspects are thinking about how do we make it available for anybody who is interested in this work related to secured computing. Thank you, and I will take questions.
Thank you, Judy. Appreciate the talk. So let's open the floor for questions. One question I had, and this was not clear, likely for me, is what I understand is that when you talk about privacy preserving, you're trying to understand how you can use next generation hardware where there's a part in which secure computing can be done and a part that secure computing cannot be done. And you're trying to break your workflows into these two parts. Is that a right interpretation of your work? And so somebody will have to take the program and annotate it saying that this part has to be done in secure area and some which is not, and then you find the best way to partition it. Am I understanding it right or missing the point?
Yes, I think you're correct on that. How to port legacy algorithms and models into this framework with minimum change. Is that my understanding?
Right, okay.
Yeah.
So when you do genomic computation, parts of it which have to do with, say, looking at personalized data in a very specific form, you might end up doing it in the secure part of the code, processor code, and the others would be then done in a different form. This part was not super clear to me. I'm sorry if that's the case.
Yeah. So let me try to go back to the main idea here, the framework part. A lot of the secured-based computation is hard to generalize because it's very specific to the data and to the algorithm itself. So here, by leverage using the secure, insecure containers, we can generalize by partition the secure versus non-secured tasks. So if we have all of this separation from data to task, we can orchestrate using this framework. So this is where the key idea of this work.
Okay, thank you. Other questions?
Yeah, I have a question, Mrs. Stephen. This is a silly question, but how do you convince the users of this software that it's truly privacy preserving? So if I wanted to analyze my own genome, for example, what do I have to do other than walk through the entire code?
Yeah, that's a great question here. This basically related to the conventional method we had here. You need to know this part, which is a subset of data really has security issue. Because you know your application, you know what data need to be protected. For example, personal genome needs to be protected. In the space of healthcare, the patient data need to be protected, patient records, but not all data need to be protected. So that separation should be known by the users. So in that case, that separate data related to the computation can be identified. And so we can use different container to execute them, as simple as that. Does that answer your question?
I think so. So I can put my data in a container that I know is secure.
Yeah.
And then it seems there's an aspect of trust me though, that somehow I'd like to be able to verify that your code is not going to take my data and just send it somewhere else.
Oh, I got you. Fair enough. So that is actually a common problem. People unwilling or reluctant to put their data on the cloud. It's a huge problem. You can see there, if you send your data on the cloud, you don't know who will be able to, to get it. So the computation is not secured. What happened here is that between you as the user send it to cloud, we have this whole level of protection. Your data in first place will be encrypted and sent to this middleware. And in there, your algorithm, which that part is need to be protected with the data and the algorithm itself, will be executed using SQL and the graphing, which can port lexicon without changing your code, and will be executed on the secured container on SGX within the enclaves. So if you see the whole workflow from the top, from your user code and the data, and it's going through the whole stack and to the cloud. So this whole box in the middle is hardware level protected.
Okay, thanks.
The work itself, I think incorporate into, in the next step, I think incorporate into, we need to evaluate the performance. What are the boundaries? So it's a new architecture, they're coming in, and we want to evaluate how practical and feasible for common workload. And if there is any privacy preserving, data security issues, we wanted to verify that using this whole framework.
Thanks, Judy. Thanks, Gordon.
Thank you. If you have any questions, just contact me by email. Thank you.
Yeah, bye. Thank you.
Everyone.